Hello everyone, welcome to the third lesson in this course, Introduction to Stata. The third lesson is about restricting commands. So we've learned a few commands, we've learned how to open and use Stata, and now we're going to learn how to restrict those commands to subsets of data, either based on the position, so whether it's the first 10 observations or the last 100 or what have you, or based on an expression of some kind. So is this variable higher than 40? Is this variable equal to 12? And combinations thereof. We're also going to go through some more interesting commands that are hopefully going to be useful. Okay, so first things first, let's load in the dataset from the end of the last lesson, so lesson 02 underscore your initials, or load in the lesson 3 dataset. They should be the same, so pick whichever one you're comfortable with. Okay, so we're going to jump straight in with the in qualifier. So there's the if qualifier and the in qualifier. The in qualifier is for observations that are in a certain range, whereas the if qualifier is restrict commands to observations if something is true. So in 3.1. In allows you to restrict commands to a range. Ranges in Stata are expressed by saying, we have our command, we have variables, potentially variables that go with the command, and then we say in, the range is specified as one number slash another number, meaning the first number to the second number, 1 to 2, or the first observation up to the 200th observation. So it's one number slash another number. The slash means 2 to Stata. For example, if you wanted to list ID and age, but only for the first 10 observations, we would say list ID age in, not ion, in 1/10, 1 to 10. And instead of listing all 1,000 observations for ID and age, it's listed just the first 10. A couple more examples, list ID age in, let's say, 15 to 200, and that should have listed every observation from number 15 up to number 200. Okay, we can also express the range as being the number of observations from the end. So if you wanted the last 10 observations, we could list ID age in -10, meaning the 10th observation from the end, that's what the minus number means, to -1, which is the first observation from the end, which is the last observation. There we go. So it's listed observations 991 through to 1,000, because that's the 10th observation from the end up to the last observation. We could also say the last 5 observations, list ID age in -5 to -1, last 5 observations. One last example, ID age in -50 to -10, or -10, and it's given us the 50th observation from the end, all the way up to the 10th observation from the end. Okay, there's a couple of special characters when using in, or when expressing ranges in general. If we wanted specifically the first observation, we could use the letter F, standing for first, and if we wanted the last observation, we could use the letter L, standing for last. And we could even write the word in if we're using an in restriction. There we go. So F just stands for first, L stands for last. There's no difference between doing this and saying 1 to -1. I think it's generally preferable to say 1 and -1 when meaning first and last, because I think it's more understandable. And L's in Stata, unless you change the font, look suspiciously like 1s. It's very hard to tell. But there we go. Two main limitations using in. So the first is that you can only specify a single range. You can't specify multiple ranges at once. So you can't say 1 to 10 and 15 to 70. It's just one at a time. The second limitation is that in is entirely dependent on how the dataset is sorted. So if we look at the dataset, it's sorted by ID. As far as I know, there's no way actually to tell how it's sorted other than by looking, but it's sorted by ID. So if we changed how the data is sorted, say by age, then the first 10 observations can be completely different to the first 10 when it's sorted by ID. That said, let's sort the dataset. So 3.2 is about sorting the dataset. It's pretty simple. So the command is just sort, and then we specify the variables we want to sort by. So if we did want to sort by age, we would just type in sort age. Nothing comes up, but if we click on the view, we can now see the age is sorted from lowest number up to highest number, and then we've got the 999s there. The 999s, incidentally, are the missing numbers, and that we'll be replacing those with actual missing numbers once we go on to the if statements. Okay, so sort, you can specify as many variables as you like when you're sorting. So it doesn't really make sense if you're using a continuous variable first. Age isn't strictly continuous because it's sorted by, it is only to the nearest year. But if we sorted by height, there'd be very few instances where sorting by another number would actually change how the data is sorted. So when we use multiple variables in a sort command, it's usually because they're categorical. So let's try sorting by hair color, then accommodation, and then age. So this will sort everything by hair color. Then within each group of hair color, or each color in hair color, it's going to sort by accommodation. So that's the own, rent, and mortgage. And within each of those is going to sort by age. So let's do it. Take a quick look. First thing we sorted by was hair color, which is here. So it's done the blanks first. In string variables, blanks come first when sorted alphabetically, because a blank comes before any other character. In numbers, sorted it is sorted from minus infinity to 0 and then positive infinity. So minus numbers first, then positive numbers. At the very end are the missing numbers, because if you remember, missing numbers in Stata are actually stored as a number very close to infinity. So hair color first. Good. Black, blonde, brown, grey, red. Fine. Hair color, then accommodation. Where is accommodation? Here it is. So within each hair color, it's sorted by the accommodation variable, and within each accommodation variable within each hair color, it's sorted by age. So you can see, if we select those, within own for the blank hair colors, age has now been sorted lowest to highest. Same within mortgage, same within rent, and it will do this all the way down. Okay, sort can only be used for lowest to highest and alphabetically. There is another command called gsort where you can reverse sort, so highest number to lowest number, or highest positive number down to 0 and then down to the largest negative number, and sorting Z to A instead of A to Z. Should also mention that in Stata, capital letters come first and then it's lowercase letters. So if we sort, let's just sort again, but by sex this time. Sex has a combination of capital letters, so capital F females, capital M males, and also lowercase f females and lowercase m males. There's no functional distinction between the two, it's just that's how the data was entered. But when you sort, capital letters come first and then lowercase letters. Okay, so to reverse sort, we use gsort. Gsort isn't reverse sort. Gsort by itself, if we gsort id, acts exactly like sort does, but what gsort does allow us to do is we can gsort by negative variables, which means reverse sort this particular variable. So if we wanted oldest to youngest, we use gsort, not sort, and we put a negative sign in front of the variable that we want to reverse sort. So you can see age, no longer sorted lowest to highest, it's highest to lowest, all the way down to 20. Okay, and gsort you can also use as many variables in the command as you like. So gsort, let's sort by reverse hair color, then accommodation, and then reverse age. So kind of flipping some of them, but not all of them. Reverse hair color, accommodation as normal, reverse age. Let's take a look. So hair color, it now starts with red, and then goes down to black eventually, and then the blanks. Accommodation now starts at own, and then mortgage, and then rent, because this hasn't been flipped, unlike the others. And within each level of these, we have ages, and ages are reverse sorted to start at the highest number and go down to the lowest number. Okay, we actually don't really want any of that, so we're going to sort back by ID, so everything looks standardized. Good. But that is how you sort in Stata. While we're sorting, we may as well talk about ordering as well. So 3.3 is ordering variables. Sorting affects observations. Ordering affects variables. So ordering actually makes very little difference in practice to how Stata operates. There's very few advantages to ordering variables, apart from it can make it much easier to have a look and see what variable is called, and it keeps the data set tidy. So I like to keep all the variables as similar together. So height and weight I usually kept together. Ideally I want BMI to go with height and weight because they're related. Whilst we got ID, usually I put first. Age and sex are usually pretty high up in the list. If I'm working on data sets that have a lot of exposures and a lot of outcomes, I usually keep the exposures together, the outcomes together. It just makes it easier to kind of manage the data set. But it's certainly not necessary, and it doesn't really affect how Stata operates. Sort, however, does, in various cases, affect how Stata operates, and so it's good to know. Okay, so order. There are many ways to use order. The kind of simplest way is you just specify every variable and you specify it in the order that you want it to appear, both on the right-hand side, going down, and from the left to the right on the spreadsheet view. So, for instance, if we wanted to have BMI appear after weight, we could say order ID, then age, then sex, then height, then weight, and then BMI. We can stop there. We don't need to order anything else, because the way Stata orders, it does everything that you've listed, sticks it at the top, and then leaves everything else as it is. So because ID, age, sex, height, and weight are all there already, they're not going to move. They were already specified first. But BMI is going to be brought in below weight, or indeed to the right of weight, and everything else is going to stay as it is. So we click enter, BMI is moved, everything else has stayed where it is, and we can see it's moved. However, that is not the most efficient way of doing this. You might have hundreds of variables and it will take you forever to write them all down in the order that you want. So if you only want to move a single variable in your data set, we can use the order command again, but we just specify the variable we want to move. So average BP, let's say we want that to go before systolic blood pressure. We then use the order command, but we give it an option. And the option is simply before, and then the variable we want average BP to come before. So command is order, the variable we want to move, average underscore BP, and then as an option, so after a comma, before the variable we want to come, average BP to come before. Click enter. Average BP moves. It's now nicely grouped with the other blood pressure measurements. And we only had to type in 2 variables with the before option to get it to move. Equally, let's say we're not happy with that. We want to change where it is again, but we want it to come after a different variable. And this time we want it to come after diastolic blood pressure. So same command, but with the option after instead of before. And you can see it's moved after diastolic blood pressure. After and before can be shortened, so I can just use A and B. Just A for after, B for before. We could also sort variables alphabetically. In general, I don't do that because I like to group things by similar variables. And ordering is one of those commands where if you do it wrong, you can fix it, but it's going to take you ages to fix, because if you sort alphabetically and you want to go back to how it was before, there isn't anything else you can do but put in a manual command ordering with order and then every variable exactly how you want them after that. Or you could give up and reload the dataset. So I will go through ordering alphabetically, but I will do it in a little bit because section 3.4 is about preserving data. So I've said a fair few times now, there's no undo button in Stata. You can't undo anything that you've done. But what you can do is preserve an instance of your data set. So at this point in time, preserve it, keep it in memory, do whatever you want to the data set, and then if you're not happy, restore the preserved version. So it's not saved, it's not on your hard disk, and it doesn't appear in any folder, so it won't appear in the folder that you're working in, but it is in your Stata memory and can be recalled in case you mess up. There are uses beyond just making an error and having to reload or restore the data, but the typical use is that you would preserve, do some stuff. If it went wrong, restore, preserve again, do some more stuff, see if it goes right that time. So it allows you kind of a sandbox type approach where you can do things to the data that you're not quite sure about, and you can always restore the data set if things go wrong. One thing to note, anyone using a do file, preserve is a slightly strange command in that it doesn't work in a do file except while the do file is running. So, there we go. If I were to preserve the data set, and the command is just preserve, so you preserve a data set, and then I had a whole bunch of commands here, but I had no restore, or something went wrong, if there was an error in one of these commands, then at the point that Stata preserved the data set, it would then reload the preserved data set instead of following in with all the following all of the other commands. So your data set is only preserved up to the point either something goes wrong or the do file ends. At that point, the data set is then just reloaded as if you had restored it. So for the purposes of this coursebook, whenever we're using the preserve commands, so it's just for this section, do it in the command window, because otherwise it won't work in the do file, or it won't work as expected in the do file. We're going to meet this again when we're using macros, which is an interesting and very useful function of Stata, but it has slight differences between using macros in the command window and using macros in a do file. So moving on with preserve. So all we need to do to preserve a dataset is type preserve. Stata doesn't say anything, and as far as I know, there's nothing to notify you that a dataset is preserved, other than if you try to preserve a dataset again, it says no, the data is already preserved. So once you preserve dataset, it's in memory. You then need to clear it from memory using a special option on restore if you want to preserve it again, but let's not worry about that just yet. Data is preserved. So we can now order all of our variables, so order underscore all, alphabetically. So the option for alphabetically is just alpha. We can click it, and now our variables are fully alphabetically ordered. I really don't like this. Let's look at them. It's in just a terrible state now. So not happy with this, but we've preserved the data, so let's restore it. The command is just restore, and this brings us back to the exact point where we hit preserve. So we've undone every command that happened after preserve. Okay, now we've restored, we can actually preserve again, because every restore command erases the preserve. So it brings it back from memory and gets rid of the temporary preserved data set. However, let's do the order command again. And let's try to spell alpha correctly, at least on the third time. Right, so we've ordered it again. We've preserved. There we go. So if you wanted to keep the preserved dataset in memory, we can add the option preserve to the restore command. This means that we don't need to hit preserve again. It's still preserved. So we can order again and then restore again. If you use restore without the option preserve, the preserved data is lost, or rather it's loaded into memory and then lost. If you restore with the option preserve, it keeps the preserved data in memory. Finally, we can preserve the data, and if you want to clear that preserved data, we want to wipe it from memory, we use the command restore, but with the option not. So telling Stata, don't restore this, just remove the preserved data. Bit of a fiddly one, but can very much be useful. So preserve, useful for playing with data and checking whether what you're doing works without actually losing data, and without having to reload data sets or save data sets and then reload them, save, reload, save, and reload. So it's a temporary, just in memory, save all the data that you have, they can then play with. Okay, that's it for preserve. So anyone using a do file, feel free to switch back to the do file. Preserve does work with the do file. You just need to bear in mind that if you run into an error, weird things are going to happen. And if you don't restore the data set at some point in the do file, in the block of code that you're running, then it's going to default back to the preserved data once the code has stopped running. So yeah, it gets a bit fiddly when you're using it in a do file. Okay, on to section 3.5, the if qualifier. So this is the probably one of the most powerful things we'll be looking at. If is a real, if's just really good. it restricts data to it restricts data for a command to those where an expression is true. The expression that you're looking at can be as complicated or as simple as you like. The example that we're going to go through is we can specify that a command is only applied to observations where hair colour is black, or where hair colour is not black, or where age is above 60 years, or, and this is a long one, so where height is 1.7 meters or more, and weight is below 100 kilograms, or weight is below 80 kilograms. So that's a slightly longer if statement. They can be as long as you like, and you can have as many combinations of and or as you like. So, general syntax. We have our command. We have our variables, potentially variables, and then we have if some expression. And the only data for which the command will be run is those observations where this expression is true. So where a hair colour is black, where it's not black, or where age is above 60. Okay, in the course book, in this section, there is a list of arithmetic, logical, and relational characters that Stata uses in order to differentiate everything it needs to. So most of them should be familiar. Addition is just the plus symbol, subtraction is a dash, multiplication is a star, the asterisk, shift 8, division is a /, a power order, we've seen this when we generated BMI, is the capat, shift 6. Logical ones we won't have seen before, haven't seen in this course, you may have seen them in other things. If you want something that's not equal to something else, you can use an exclamation mark and an equal sign, and that means not equal to. So 4 is not equal to 5. Or and as logical statements in Stata are expressed using a vertical line for or. So 3 or 4 are more than 2. 3 and 4 are more than 2. The vertical line is made by using left shift and the button right next to it. So just left of the Z key. I don't know if it's the same on non-UK keyboards, but on the UK keyboard it's just shift and then left shift and the button next to it. And is the ampersand, shift 7, rather than the word and. So vertical line is or, ampersand is and. Other languages, computer languages, use the words or and. Stata doesn't. Stata uses vertical line and ampersand. Possibly last thing to say is that in if statements, if you want something to be equal to something else, so if age is 22, you say if age is equal to 22. So very important, because it's a very common mistake to put in only one equal sign. In Stata, one equal sign is assignation. So you're saying set the values of age to 22, the same way we do with replace and generate commands. If we're using a statement to denote equivalence, is age equivalent to 22, we use two equal signs. So I'll be making a point of that as we go through, because it's quite important. Actual last thing to say is that if you want greater than, it's just the greater than symbol, less than is the less than symbol, greater than or equal to is the greater than sign and then the equal sign. Less than or equal to, same thing, less than sign, equal to sign. And I think we have examples of most of these things as we go through. So, examples, probably the best way to go through this. Let's say we want to summarize BMI for all people with black hair. So we know we want to summarize BMI, so let's start there. Summarize BMI. for all people with black hair. So if hair color is equivalent to, equal to black. Now, first thing to note, equal to, I'll be saying that a lot. Second thing, hair color is a string. So hair color is red, so hair color is a string. So if we want to use if statements with strings, we have to use quotation marks. So summarize BMI if hair color is equivalent to the string value black. So look, there's 183 observations of BMI where the hair color is black, and it gives us the mean, standard deviation, minimum, maximum, as it would whenever we summarize a variable. Okay, if we were to type in this command and not include quotation marks, Stata interprets this as being a variable. So you can say whether if age is equal to BMI, sometimes age might be equal to BMI, and Stata would count that as a valid if statement. In this case, there is no variable called black, and so it tells us black not found. Unless you know why this isn't working, that's a really unhelpful error message. So you just need to bear in mind, if you're using an if statement with a string, you need quotation marks. Virtually any time that you're using strings in Stata, you need quotation marks. But especially when using if statements, like this. Okay, so the opposite of saying if hair color is equal to black is summarize BMI if hair color is not equal to black. And the way we say not equal to, we can use an exclamation mark, and I always do, but you can also use a tilde if that's your preference. I'm going to stick with exclamation marks. So summarize BMI if hair color is not equal to black, and this gives us 722 observations. Let's just summarize BMI without any restrictions. We get 905. If we add 183 and 722, then we get 905. So not equal to black and equal to black, those are the two kind of choices about hair color, and they add up to everybody in the dataset. However, not equal to black, or not equivalent to black, is true for people who are missing a hair color. And generally, this is not what we want. So if we want to summarize BMI, if hair color is not equal to black, but also not missing, we use an and statement. So and hair color is not equal to missing. And this will give us, this will summarize BMI for everybody who has a hair color that's not black and not missing. And you can see there is a slight difference here. So 706 observations had a BMI value and a hair color that wasn't black or missing, compared to 722 where they just had a hair color that was not black. So running theme here is going to be wary of missing values in Stata, because when you use it in an if statement, or use an if statement where missing values could be the correct answer, so missing values aren't black, you need to specify exactly what you mean and specify exactly whether or not you want those missing values to be included or not. It's also worth pointing out that a lot of people would expect Stata to understand this sentence. Summarize BMI if hair color is not equal to black and not equal to missing. But Stata doesn't understand that. For every part of an if statement, so everything that's separated by an and or an or, you need to specify the variable. Stata is not happy when you specify the variable for the first part but not the second. Although this would make perfect sense to a human, it just doesn't to Stata. So if hair color is not equal to black, and it very much needs a variable to be put in here to understand what you're trying to say. This is also an unhelpful error message, because if you don't know what to expect, then equals quotation mark invalid name would mean literally nothing. But if you see it, just check to make sure that you've put a variable in every part of your if statement, even if you don't think it would need it, because a human would understand what you mean. Okay. We're going to come back to if statements in just a bit, but a quick detour into missing values. So 3.6, missing values. So missing values in numeric variables are represented by full stop. We can see those here, 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 full stops. And in strings, it's represented by a blank space. The blank spaces aren't too much of a problem. We just need to be aware that they're there. If we want non-missing values in numeric variables, then we just need to use a full stop to indicate that we want missing data. So summarize BMI if weight is not equal to missing is some BMI if weight is not equal to full stop. If you try to put in the same thing that we put with the strings, so an empty string, blank string, is 2 quotation marks. But if you try to do that for a numeric variable, Stata gets confused. It says there's a type mismatch because the type of variable that weight is numeric, and you've tried to put in a string, or we've tried to put in a string variable here. Weight needs a full stop to indicate a missing value, whereas hair color, being a string, needs the 2 quotation marks to indicate a blank string. So, age, let's just sum age. Age has several values that are 999. This should be missing. So someone has coded this data so that 999 is used to represent a missing value. But to Stata, that just means that person is 999 years old. Which is unhelpful because it's going to use it in any calculation that we do. So if you wanted to work out their age in months, then their age in months is going to be 999 times 12, which is pretty big. So what we need to do is build up a little bit of code and work out what to do. So we want to replace these values of 999 with missing. So first things first, we know we want a replace command, and we know we want to replace the values of age. And actually, we know we want to set those values of age to missing. If we were to just use this as the command, every value of age would be set to missing. So we want to restrict it just to the values of age that are 999. So we use an if statement, if age is equal to 999. So we're replacing age, we're replacing the values of age with the missing or what Stata understands as being missing, but only for those values where age is presently 999. Put it in, and we can see that Stata has done 80 real changes and 80 set to missing. So normally when we replace, Stata gives us an indication of how many real changes it's made. When it sets numbers to missing, it gives us the additional information how many were set to missing. This is because there are often expressions that you can do in Stata where the result is a missing value. So if you divide any number by 0, the result is a missing value because you can't divide a number by 0. There are other types of mathematical expression that result in missing data, and Stata likes to tell you that just to make sure you know what you're doing. In this case, we were literally setting values to missing, so this is fine. 80 real changes made, 80 set to missing. If we summarize age now, only 920 observations appear, so that's 80 less than 1,000. The mean is 50, the minimum is 20, the maximum is 80. That makes way more sense than having people who are 999 years old in our dataset. Okay, a few more examples. So let's say we want to count the number of people who are over 60 years of age. We could summarize again with an if statement. So if statements can go on to almost all commands, and then the command is restricted just to those commands. Some commands don't take if statements, but you'll definitely know about them when you try to use them. Okay, so we could summarize, but we could also use the count command. So count command, it just counts a number of observations. If you just put in count, it counts the total number of observations, but you can use it with if statements. So if we wanted to count everybody who is over the age of 60, we can say count if age is greater than 60. And we can answer 387. So certainly Stata thinks there are 387 people who are older than the age of 60 in our dataset. But if you remember back to the missing values section, a missing value is a number in Stata that is very close to infinity. For most practical purposes, it ignores missing values. So if you're calculating, so when we calculated BMI, it ignored the missing values of height and weight and gave them a missing value in BMI. But in if statements, age is more than 60 if it's missing, because missing values are stored as a number close to infinity. So we actually need to be more specific when we're using the greater than symbol in any numeric expression where there is likely to be, or any chance of being, missing values. Instead, we still want to know whether how many people are above the age of 60, but we also want to specify if age is not equal to missing. And when we do that, the number of observations drops quite a lot. So there are 80 missing observations for age, and those are counted if we don't specify not equal to missing, and not counted if we do specify not equal to missing. Okay, last little bit about missing values. So just a single full stop, that is Stata's usual way of coding a missing numeric value. But there are 27 different types of missing value, from a full stop to .a, .b, .c, .d, all the way up to .z. Each one of those missing values is incrementally higher than the other. So the full stop is the lowest missing value, and .z is the highest missing value. The point of having all of these missing values is that a full stop might represent a certain kind of missingness. So the examples in the course book are that one missing value might be I don't know. So they're asked the question and their response was I don't know the answer to that question, which is different to a missing value because the question wasn't asked because the interviewer ran out of time. And that's different to a missing value because the person inputting the data couldn't read the value on the form. And that's again different to someone's age being missing because a page of a form was lost. And all those reasons for missingness may be relevant and they might be useful in determining how to analyze the data. So a single dot could mean one thing, .a might mean another thing, .b, .c, .d, etc. They might mean different things. And you can store all of those while also maintaining the missingness. So Stata will treat all of these values as missing, won't use them in calculations, but in this above statement, count if age is more than 60 and age is not equal to a single full stop, won't include any values that are .a, .b, .c, etc. So, to get around this, and in every future example where this comes up, what we actually should, and the best practice is to say, age is less than missing. And that covers every possible missing value in Stata. That is coded as missing. It still wouldn't do much about getting rid of the ones that are coded as 999, but we fixed those already. So no change here because there are no .a's, .b's, .c's. And if you know your dataset doesn't have them, it is fine to use not equal to missing. But if the dataset came from someone else, or if you're just not certain and just kind of save your time in checking because it's not relevant, then use less than missing. Every future example in this coursebook will use less than missing rather than not equal to missing for those reasons. Okay, section 3.7, continuing with the if qualifier. So the final example that I gave way back when we were going through the if statements was summarizing age if either height is 1.7 meters or above and weight is below 100 kilograms, or weight is below 80 kilograms. And an or can be combined as many times as you like in an if statement. It just makes it more complex to understand what's going on, so you need to be very clear about what you're telling Stata. And we'll go through a little bit of how to check that what you intend to happen is actually happening. Brackets are usually very helpful. So brackets in these expressions tend to go where you take a pause in breath to kind of really get across what you're trying to say. So we'll turn the if statement into Stata code. We know we need to sum age, that's fine, we've done that before. And then we need an if statement. The if statement needs to be true if either of these conditions is true. Height is above 1.7 meters or over, and weight is below 100 kilograms. So that's one statement that will have an ampersand in it. The second thing that could be true, to cause a whole statement to be true, is that weight is below 80 kilograms. So we have height is 1.7 meters or over, and weight is 100 kilograms, or weight is below 80 kilograms. And to make things easier, I'm going to put brackets around each of those different parts to kind of separate them. So the Stata code for this, the first statement, we want height to be equal or to 1.7 or over, so greater than or equal to 1.7. We have to remember about the missing values, so height is less than missing, and we need weight to be less than 100. This is one statement that can be true to cause the if statement to be true. So that's one part. And then we have or, going to put this in brackets. Stata doesn't need this to be in brackets. It's just for clarity for us to see the two parts separated in brackets. Weight is less than 80. So this is the entire if statement. Nothing will happen if I run this now because it's not a full command. So let's add in the actual command. So the command is summarize. The variable is age, and our if statement is here. So if height is greater than 1.7 and not missing, and weight is less than 100 kilograms, or weight is less than 80, and we click enter, and it tells us that 757 observations have values of age that fit this criteria. So how do we check whether this is actually showing us the right observations? Because we might have made an error, we might have got the brackets in the wrong place, we might have got the ors and the ampersands around the wrong way. Anything could happen to make it not be correct. One way that I like to do is create a new variable that only has a value if this statement is true. So let's generate a new variable called x. I often use x as a new variable because I know if there's something in my dataset called x, I can just ignore it. I've created it to test something. And so it's not a proper part of the dataset, and I can remove it at any time without there being a problem. If I called it something else that's meaningful, I could call it temporary or temporary variable. But x just saves time when I'm in a hurry trying to test my code. So I want to generate x, but only if this statement is true. What this will do is generate the new variable x, and it will generate it equal to 1, so that's fine. But any variable, any observation that doesn't fit this criteria will have a missing value instead. So we generate it, and it tells us 170 missing values were generated. Now, this isn't the same number as the number of missing values here, because we're only summarizing age. Age has missing values all by itself. So we expect there to be fewer observations here than there are observations that are going to have x equal to 1, because age has missing values. So even if the observation fulfilled this criteria, it may have had a missing value for age and therefore not be summarized. Let's now take a quick look at the variable we just generated. Okay, there it is, and it's got 1s in some places and missings in others. Missings are only when this if expression isn't true. What we can do now is list height and weight and the temporary variable in, let's say, the first 10 observations. And we see that we get the heights, we get the weights, and we get whether or not the variable was created. You can think of this 1 as being, yes, this observation satisfies the if statement that you just gave, and the missings as this observation does not fulfill the expression that we just generate, the if statement. So let's just go through the first 5. Height of 1.66, weight of 61. What we want is the height to be more than 1.7 and not missing, and the weight to be under 100. We can check, is this condition satisfied here? No, the height isn't above 1.7, but the weight is below 80. So this should be included in the if statement as being true, and it is. The second observation is actually the same. The height is below 1.7, so this first part of the statement isn't true, but the weight is below 80. So as overall, it is true, and it should be included, and it is. The third observation, the height is over 1.7 and not missing, and the weight is below 100. So this first part of the statement is true. Weight is not less than 80, but that doesn't matter because the first part of the statement is true, and to be true, either the first part or the second part, or both, need to be true. For the fourth observation, height is 1.56, so this first part of the if statement isn't true, and weight is not below 80, so the second part of the if statement isn't true, so none of this is true, and so it shouldn't, the fourth observation shouldn't satisfy the if statement, so it shouldn't be included in this summary, and we know it isn't because when we generated x, a missing value was generated for this variable, for this observation. The fifth and final observation we'll look at has almost identical heights and weights to the second observation. It doesn't fulfill the first part of the if statement, but it does fulfill the second part. So it's true, so it has a 1. Good. If statements can get very tricky, and it's usually worthwhile checking whether or not that what you expected has come to pass. Checking in this way doesn't guarantee that you'll pick up any problems, so it's worthwhile trying to find exceptional cases. So you might try to find really low values of height or really high values of weight, and vice versa, and check those just to make sure that what you did worked. Okay, we finished with x now, so we can drop it. Drop x. And now we're going to use if statements to do some practical things like manipulate our data. So if we tab sex, commented on this a few times, there are uppercase and lowercase values for female and male. This isn't helpful because Stata does not understand that we probably actually mean the same thing whether or not we use a capital letter. So these are completely distinct categories to Stata. Let's change that and make everything capitalized. So what we want to do is replace some of the values of sex, and we want to replace them with the values of uppercase F female, but only if sex is equal to lowercase f female. Put it in, and it tells us 226 real changes made. This makes sense. We have 226 values of sex that are lowercase f female, and all of those will now be uppercase f female. If we tap sex, we can see that that is the case. We now only have uppercase f females. We can do the same thing with males. Yeah, let's type it out in full. Replace sex equal to uppercase f male if sex is equal to lowercase m male. 248 real changes made. That looks like it should be right because there are 248 instances of lowercase m male. Tap sex, and there we have it. Only uppercase f females and uppercase m males. Excellent. This means that we can actually do commands split by sex without worrying that we're going to get different results for the uppercase f females, lowercase f females, and uppercase and lowercase males, which is pretty much what we're going to do next. The by qualifier, section 3.8. So the by qualifier works a little differently to if and in. If and in come after the command, and they restrict observations to parts to either ranges or if an expression is true. By performs the same command for every level of a categorical variable in turn. So if we wanted to summarize age for every hair color in turn, we could write out several if statements. So summarize age if hair color is equal to black, summarize age if hair color is equal to red, brown, blonde, and grey, all in turn. But that's 5 commands, when actually we could write one command to do it all for us. And that's what using by does. So the general syntax, let's do it like this. We do it by some categorical variable. I say categorical, it will work with any variable in Stata, but if you use by with a continuous variable, what you'll end up doing is running a command on individual observations as many times as you have observations in a dataset. So by categorical variable just means this works way better with a categorical variable than it does with a continuous one. And then we have our command. So it's phrased, or the syntax is different to if and in, because the by comes first and then there's a colon, and then our command proceeds as it would. And you can use if statements with this, I believe. In statements don't make too much sense, so I don't think they work, but let's test it later. So you can also use by sort. So when you use by itself, so by the categorical variable, etc., you need to sort the data by the categorical variable first in order to get the results out. By sort completely removes that step and is therefore a much better command that I would rather use. I would never use a by command when I could use by sort. We'll go through examples of both, but just as fair warning. Okay, so we need to sort. In order to use by, we need to sort first. So we're going to sort by hair color, and then by hair color, colon, we're going to summarize age. And what this does is for every level of hair color, including the blanks, it summarizes age for us. So this is the equivalent of saying summarize age if hair color is equal to blank, if hair color is equal to black, if hair color is blonde, if hair color is brown, grey, red. And it saved us a whole bunch of typing by giving us all of these results with only one line of code. Okay, let's resort by ID, because we had to sort by hair color there, and then run the same command again, but instead of running by, we'll run by sort, and it gives us exactly the same output. but there we go. But it also sorts by hair color for us during the command. Let's sort by ID. If we try to use by without sorting first, Stata just tells us not sorted. So it even knows that it's not sorted. It just doesn't. It wants to preserve the order, the sorting that we already have in the data set. So it wants us to tell it, actually, we do want to resort by whatever we need to in order to make this command work. So it's another data preservation mechanism in Stata. Okay, by works with any number of categorical variables. So we can have any number of categorical variables before the colon. Stata will do every command by every permutation of the variables that you put in before here. For example, if we by sort sex and income, tab current smoker, so we're tabulating current smoker, but restricting it to every permutation of sex and income. So this is, let's just run it, and then scroll up through the vast amount of text. When sex is missing and income is 18,000 to 30,000, this is the tabulation for current smoker. If sex is missing and income is 30,000 to 50,000, this is the tabulation. And then when sex is missing and income is less than 18,000, this is the tabulation. And then it moves on to the non-missing values of sex. So for females, and when income is missing, it gives us this tabulation. Female income at a different level, this tabulation. Female income at a different level, tab. Female different, and it keeps going. When there's no observations, where sex is equal to one thing and income is equal to another thing, it doesn't show the results. So we scroll up. Sex is equal to missing. There's only 3 levels of income shown. So the 50,000 plus level isn't shown because there are no observations for which sex is missing and income is £50,000 or more, or indeed where income is missing. So it doesn't show those, but it will go through every permutation that you give it and display the results anytime when there's data to show. So by can certainly be a very efficient use of coding if this is the sort of information you want from the data. Now when we look though, everything is sorted by sex and income, which isn't terribly helpful, so let's resort by ID to get back to where we started from. And finally, let's just save, because we are going to go on to the exercises now. 3.9 is the exercises. So I will do save as again, because once again, I haven't changed my directory. Data, and then lesson 3sh. I ran through all these earlier, which is why it still exists. So let's save. Yes. Very good. So this is now saved, ready for the 4th lesson. And now have fun with the exercises in 3.9. Okay, welcome back. Let's go through the answers. This was much more coding than the previous two exercises, so I hope you got on okay with it. Let's go through it. So part 1, change your directory if necessary and load in the exercise 2 initials, exercise2.dta dataset that you used in the last exercise, or if you're not confident, use the exercise_03 DTA file. Okay, so exercise_02_ my initials. I will also change the directory, and let's just copy all of that and get rid of the file. There we go. So my directory is now changed, so I'm in the right place. Question 2. Sort by age, then list the values of age and height together in the first 20 observations. So sort, we did plenty of that in the lessons. List age and height in the first 20 observations. So list, and then the variables, and then the in statement, 1/20, 1 to 20. Good. Now reverse sort by height, highest, lowest, and list age and height together in the final 10 observations. So reverse sorting, we're going to be using gsort, because sort doesn't cope with minuses, or reverse sorting. Gsort, reverse sort by height. Okay, and list age and height together in the final 10 observations. List age, height, the final 10 observations, we're going to be using minus signs again to indicate the 10th observation from the end and the last observation. You could have also said L here. It would have worked either way. And once again, I forgot to put the in. There we go. So reverse sorting, and now we have the minus values for height. We saw those in the last exercise, and now we actually have the means to fix those. So note anything that looks odd, it's going to be -1s of height. Sort by ID again. Okay, sort ID. Question 3. Summarize height in detail, then convert the values of height that are impossible into missing values. So summarize height in detail. The least amount we could type is probably Sue, I think H, D, but for clarity, sum height, detail. Okay, so there's actually quite a few missing values. At least 5% of the values are -1. And we can see that none of the observations are missing, which gives us confidence that -1, apart from not being possible, is also supposed to be a missing value. Okay, convert values of height. We want to use replace. Height already exists, so we're replacing height with values of missing, but only if height is equal to -1. 99 real changes made, 99 set to missing. Good. Let's summarize height with detail again. Now, the smallest values are around 1.5 meters, largest around 1.9. Makes sense to me. Question 3b. Also set to missing any value of BMI created from the impossible heights. So when we created BMI in the last exercise, we saw that some of the values of BMI were impossibly large, about 100, I think there were some. And this is because of the -1 values of height. We didn't fix those values of BMI. So if we summarize BMI with detail, we can see some of the values of BMI are fantastically large. Largest 107.8. Those weren't fixed because once a variable is generated, it doesn't change if we change the data that created it. So we changed the underlying values of height, but we haven't updated BMI to reflect that. So what we could do is replace the values of BMI with missing if the values of height are now missing. We can't say if height is equal to -1 because they're not equal to -1 anymore. They're equivalent to a missing. But if we do this, we get 99 real changes made and 99 set to missing. So that is exactly how many were changed when we changed the values of -1 to missing in height. What we could have done as well is we could have replaced BMI equal to weight divided by height squared, the same as how we created it in the first place. And that would have overwritten the values of BMI that should have been missing to missing, because in this command here, now that the values of height are missing, BMI should also be missing. It didn't make any changes here because we've already set those values to missing. If we hadn't have done that, all 99 of those missing values of height would have propagated through to the values of BMI. Okay, question 4. Yep, question 4, put BMI after weight and date of recruitment before age. Okay, that's ordering. So we're going to order BMI and we want it to be after weight. I'm going to use the shortened formed A weight. And order date of recruitment, I use tab then to make it quicker, before age. There we go, so date of recruitment is now before age, and BMI is after weight. Good. Question 5. Preserve your data set. Hint, it's possible to use a do file for this question, but I wouldn't recommend it, and then systematically remove data. So let's do it without a do file. Preserve. Remove ID, accommodation, exercise, calories, income, marathon, and smoking status. Okay, removing data is dropping it, so that's easy enough. ID, accommodation, exercise, calories, income, marathon, smoking status. Let's just do a quick check. ID, accommodation, exercise, calories, income, marathon, smoking status. So we don't actually need all of this. This will work, and this is fine. But we can use the Stata shorthand. So instead of saying accommodation and then all the variables between accommodation and smoking status, we could also say accommodation dash smoking status, all the variables between these two variables, including them, drop them all. And they're gone. Good. Now, remove everyone with red hair. Hint, remember blue variables are labelled numeric. Okay, let's just check that. So we want to remove everyone with red hair. There's someone with red hair. And in order to remove them, we're not going to remove them like we would have done in the lesson data set, because these aren't strings. These are numbers that are labelled to look like strings. So the value of red hair is actually 5. So we're going to use drop, and to remove observations, we just say drop, and then if hair color is equal to, and 3. Oh, no, 5, it's 5. Ooh, 3 is blonde. Drop if hair color is equal to 5. Let's just make sure we're doing the right thing. Tab hair color. Our command, drop if hair color is equal to 5. Tab hair color again. And we've gone from having 141 people with red hair in our data set, dropped now, so 141 observations deleted, and they don't appear in the tabulation. So we're down to 1,320 people who have a value of hair color. If we just do a quick check, we're actually down to 1,359 people. Good. Now, remove everyone who isn't female, lowercase or uppercase, because in this data set, our values, they haven't been fixed yet. They've been fixed in the lesson data set, but not the exercise one. So we still have, annoyingly, upper and lowercase values. So remove everyone who isn't female. For this, we can assume that if a value is missing, they also need to be removed because they aren't female, or at least they might be female, but we don't know that they are. So we're going to, in this case, we can keep if sex is equal to female, or sex is equal to lowercase f female. And this will keep in the dataset anyone with a value of sex that is uppercase F female or lowercase f female. Do that, 688 observations deleted, that's quite a few. Part D, keep the age and diastolic blood pressure variables only. Okay, keep age and diastolic BP, easy enough. Just down to the two variables now with no one who doesn't have values of female or female, although we've deleted the sex variable now. Okay, remove everyone whose age is higher than half their diastolic blood pressure, as well as anyone with missing values for either variable. That's quite a mouthful. Okay, so remove everyone whose age is higher than half their diastolic blood pressure. Drop if age is higher than half their diastolic blood pressure, so diastolic BP divided by 2, and anyone who has missing values of either variable. So let's add in an or here, or diastolic BP is more than or equal to missing. I can't remember whether this is necessary or not. Let's find out. So everyone whose age is higher than half their diastolic blood pressure. Is there anyone else? Yes, there are people left with missing values of diastolic blood pressure. Because half of infinity is still infinity, or number close to infinity is still close to infinity. So age is not higher than a number close to infinity divided by 2. But we can drop those people anyway. So anyone with a missing value or higher, so a single full stop missing value or higher, was now dropped. So everyone in this data set now, this quite restricted data set, has values for both age and diastolic blood pressure. Part F, count how many observations you have, then restore your data sets. So count 189, fine. Could have done that also by looking here, or summarizing, because we know there are no missing values in our data set anymore. And then restore the data set. So restore, and we're back up to all of the data, which is quite nice. Good. Question 6. Summarize age for people who have black hair or are shorter than 1.7 meters and female, lower or upper case. Just note in part A, this may be tricky to check whether you've put in the right code by creating a temporary variable, including the if statement and checking some observations. This is the part where we created the temporary variable called x in the lessons, and then drop the temporary observation. Okay, so let's start with what we know. We know we need to summarize. So summarize age, and then we need an if statement. The if statement is going to be pretty long. We want the hair color to be equal to black hair. Let's take a quick look. Black hair is 1, so actually you probably could have got that from this part up here. Black hair color is 1. Okay. Or, and let's put that in brackets as well because we know we'll need them, or are shorter than 1.7 meters and female. So, or height is not equal to shorter than 1.7 meters, ampersand, and female. So this part is what might have caused some problems. Because female is upper and lowercase, we actually need an or statement to come in here. So if sex is equal to female, or sex is equal to female. So this looks pretty complicated. The first part's simple enough. If hair color is equal to 1, this is corresponding to black hair. Then we need to know, height is less than 1.7 and sex is female. But because sex has 2 versions of female, we need to put in brackets an or statement that counts both of them. Click enter and we get 747. If you miss out the brackets here, So the brackets around the or statement, let's just do it and see. There we go, we get more observations because Stata is interpreting this part as saying height is less than 1.7 and sex is uppercase F female, or completely separately, sex is lowercase f female regardless of their height. So this is actually more inclusive as a statement than the one above it, because the lowercase f females don't need to be lower than 1.7 meters in order to be included in this particular command. It can certainly be difficult to see exactly what you'd need to write in order to get this precisely as we would expect. So let's generate that variable, and the temporary variable, and see whether everything is as we expect it to be. We already have the if statement here, so all we need to do is generate value of x equal to 1 if, and then the same statement. It very much needs to be the same statement for this to work. 686 missing values generated. Okay, that's fine. And then let's just have a look in the first, say 20, 10, 20, 50, it doesn't matter. Just some observations to check whether or not this is working. So the pertinent factors, don't include age, in fact. Pertinent factors are hair color, height, and sex. And we need our temporary variable as well. Let's say we want the first 20 observations. Okay. So anytime hair color is equal to 1, x should be 1. So let's just take a quick look down. Black hair color, x is 1. 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 Okay, that seems to work. We also need to look at height less than 1.7 if the observation has a sex equal to either uppercase or lowercase f female, and height less than 1.7 in all those, and x equals 1, good. Let's check these. Hair color is not black, and they're not female, so they're not included in the if statement. Good. Hair colors are missing here, but they're both female and have a height less than 1.7, so are included. Black hair color and female and less than 1.7 meters, so included. Blonde, but less than 1.7 meters and female, included. Black hair, so included, even though the height is missing. All of these three are female with a height less than 1.7, so are included. This person here, blonde hair and male, so not included, fine. Blonde, but female and less than 1.7 meters, good. Male without black hair, so not included. Black hair, so included. Red hair and male, so not included. Red hair and female, but less than 1.7 meters, so included. And finally, grey-haired male, so not included. That all looks fine. So we can be at least reasonably sure that our if statement up here was correct. Not that one, sorry, this one. So this if statement was correct. Okay, we could also browse, not sure I mentioned this before. When we want to browse the data, we can either click on these buttons up here, or we can type browse or edit, and it brings the same screen up. So we could look through as many examples as you like to make certain that the code is doing what you want it to do. Now we've done this, let's drop x because we don't need it anymore. Okay, question 7. Fix the sex variable so all observations start with a capital letter. Now, wouldn't it have been nice if we did this before we did all this tedious stuff? I'm sure it would, but then you wouldn't get these nested and bracketed statements that are so fun. Okay, so fix the sex variable so all observations start with a capital letter. We did this in the last. In the lesson. Sorry. So replace sex equal to uppercase F female if sex is equal to lowercase f female. Go. And let's do the same thing for males. And let's tab sex. And there we go. Everyone has a capital letter. Good. Question 8. Tabulate sex and marathon if BMI is more than 25. Okay, so tabulate sex and marathon, easy enough. And then if BMI is more than 25, if BMI is more than 25. This particular statement actually translates to English pretty well. So not everybody has a BMI over 25, so we only have 826 observations, and this is including all the people that have missing values of BMI as well. So we might want to also specify and BMI is less than missing. Because remember, if BMI is more than 25, if BMI is missing, it is more than 25. So in fact, instead of the 1019 observations, we actually have 920. Okay, question 9. Using if statements, create a variable called BMI categories, which is equal to 0 if BMI is less than 25, 1 if BMI is more than or equal to 25 and less than 30, 2 if BMI is more than or equal to 30, then define and apply a value label for BMI categories, showing what 0, 1 and 2 mean, and give the variable a label 2. Order the BMI categories after BMI, and make sure you check to see if you generated BMI categories correctly. That's a lot of work. Let's go through it. So first things first, we want to generate a variable called BMI categories. We know that. And let's start with the first category. We want it to be 0 if BMI is less than 25. Okay, that's fine. 1,120 missing values generated. If we take a look at it, we can see some values are 0, but a lot of missing values. And if we check, it's because all of the values of BMI more than 25 are missing. That's exactly what we want. So it's a good start. Now that we have generated the variable though, we can't use generate anymore, we have to use replace. So if we want to replace the categories equal to 1, if BMI is more than or equal to 25 and BMI is less than 30. So that's the second category, or category 1. It's generated some changes, but we're not done yet. Replace BMI categories equal to 2 if BMI is more than or equal to 30 and BMI is less than missing. This is quite important, and yeah, missing values are more than 30. So 221 variable changes made. What we should now have is values of BMI categories for everybody who doesn't have a missing value of BMI. If you have values in BMI categories that are 2, because you forgot to put the last part of the command in, or the last part of the if statement saying BMI less than missing, then yes, that isn't quite right. There we go. But it's a very common thing to do. So we then want to create category labels for those. So we have 0, 1 and 2. And if you remember from the last lesson, this means we need to define a label. I'm just going to call mine BMI categories. You can call yours whatever. Where 0 is equal to less than 25. 1 is equal to 25 to 30. And 2 is equal to 30 plus. Like so. We've generated the label, but we haven't applied it to the values yet. So they're still zeros, ones, and twos. So we want to label the values of BMI categories with the label BMI categories, or whatever the label you generated here is called. And then we can take a look at it, and it's labeled. Good, good. Let's quickly tabulate it as well. And good. So we got our categories defined. Now we want to label the variable, because we've generated our variable, BMI categories, but so far it's missing any label. So label variable, BMI categories, and when we're labeling the variable, we just put it in a string, and this time we're going to say categorical BMI. You may want to put in what each of the numbers mean, 0 equals less than 25, etc. That would be more informative, but we have them defined in the labels, so it's not too necessary to put them in the variable label as well. Final part, we're going to order BMI categories. I'm going to order it so it's after BMI. There we go. So BMI, then BMI categories. There we go, BMI, then BMI categories. And we could just take a quick look at some of these. 25 is between 25 and 30, 31 is more than 30, 24 is less than 25. These all look right, so we can be pretty confident that what we did worked. Okay, question 10. Use tabulate to find out what percentage of people earning £30,000 to £50,000 are female for each level of BMI categories. So that is quite the mouthful again. So what we want to do is, by every level of BMI categories, we want to do something. So we use a by sort command, or a sort and then use a by command. BMI categories, colon. We want to tab sex and income, and we want the option col here. So what we actually want to know, oh dear. What we actually want to know is the percentage of people earning 30 to 50,000, so that's this column here, are female for every level of BMI categories. So let's scroll up. For BMI categories less than 25, the percentage of people who earn £30,000 to £50,000 who are female is 54.24%. For the BMI category 25 to 30, the percentage is 40.74%. For BMI category 30 plus, the percentage is 60, dead on. And for missing, where the BMI category is missing because BMI is missing, the percentage is 63.64%. Yeah, you could have done this with if statements. It just would have taken you slightly longer than using a by sort statement. Common theme with data is you can do things numerous ways. Almost everything can be done in more than one way. Some ways require less typing than others, and some ways make more sense to you than others. Given a choice between something that makes sense and something that's quick, do the thing that makes sense. It's just better that way usually. Okay, so question 11. Create a new variable, sex2, which is a labeled numeric version of sex, ordered after sex, and give it a variable label 2. This is also quite a lot of work. Okay, so we want to turn sex into a labeled numeric version of itself. There is actually a command to do this, but we're going to do it the long way using the skills that we've learned in this lesson. We'll in fact use the command that does it for us in the next lesson. Okay, so first thing we want to do is generate a variable called sex2, which is equal to 0 if sex is equal to male. These numbers don't matter particularly because we're just generating a numeric version where each number means a different thing. So you could have used 1 and 2, you could have used 1,079. It doesn't matter as long as you know, and the variable, the value label that you apply to the new variable knows what each of your numbers means. So I'm going to use the value of 0 to mean male and 1 to mean female, but the numbers themselves don't matter. We've generated variables, so we need to use replace now. So replace sex2 equal to 1 if sex is equal to female. And let's just check I did that right. So we can tabulate sex1 and sex2 and make sure all the missing values are there too. And we can see missing values for sex, just blank strings, are numeric missing in sex2. Good. Females are all coded as 1 in sex2, and males are all coded as 0 in sex2. Good, so everything is distinct. Okay, we now want to label. So label define, and I'm going to call it sex2. You can call it whatever you like. Where 0 is equal to male and 1 is equal to female. We've defined it. Now we need to apply it. Label values sex2, sex2. Good. So let's tab sex and sex2 again, with missing values as well. Missing, you actually only need mi, I think. So it works if you don't spell it out in full. So missing is still missing, female is female, male is male. Good. We then want to label the variable. So we're labeling sex2, labeling a variable. Oh dear. Variable sex2, sex. I'm just going to put in brackets numeric. As long as it makes sense to you, that's fine. So sex2 is now sex numeric. And we want to order it after sex. There we go. So now we have two variables, sex and sex2. One is a string, one is a labeled numeric variable. The labeled numeric variable is almost always going to be more useful than the string variable because Stata uses numbers more than it uses strings. Okay. Question 12. Change the values of smoking status so that 0 equals no and 1 equals yes. Check the variable label to see which is which currently. Then update the variable label to reflect the new number and meaning. And then B, create a label where 0 equals no, 1 equals yes, then apply it to both smoking status and marathon. Okay, so let's just label list. So smoking status. Check the variable list, not the value list. Yeah, okay. Smoking status. 1 equals yes, 2 equals no. Let's take a look at them. Smoking status. 1 equals yes, 2 equals no. Fine. We want to change some of those values. So replace smoking status equal to 0 if smoking status is equal to 2. Because we want all the no's to become zeros, so we want all the 2's to become zeros, like so. Tab smoking status, we only have zeros and ones now. This variable label now doesn't make sense. This is why we'll have to update it in a little bit, and why it's better to keep all this together and do everything at once, because otherwise if we come back to this in a week, we're going to be very confused. There are no values of 2's, we only have values of zeros. So label variable smoking status where 0, I want the comma, where 0 is equal to no and 1 is equal to yes. There we go, so that's updated. Now we're not going to forget what happened. We tab smoking status again, 0 equals no, 1 equals yes. Good. We're now going to label it. So label define. We're doing a general label now. This isn't specific to smoking status. This is a yes-no label. So zeros are always no, ones are always yeses. So we may as well define it. Call the label just yes-no or something else that's meaningful, because it's not specific just to smoking. But 0 means no, 1 means yes. The capitalization here is just for me, really. The capitals aren't necessary. I just like them. Label define yes, no, and we want to label the values of both smoking status and marathon with the label yes, no. So remember, when you're labeling values, you can just put as many variables here as you like, as long as it's ended with the label that you're trying to apply to all of them at once. So you could have split that into 2 commands if you wanted. Let's take a quick check. Tab smoking status, no and yes, good. 0s are no's, 1s are yeses. And tab marathon as well, and they're all no's and yeses as well. Good. question 13 is, we've made a lot of changes to the variables now. Check all the variable labels and fix any that aren't correct. Okay, let's have a look. We've got ID number, fine, date of recruitment, age in months. If you remember back to the last exercise, we changed that. So age is now in years. But of course the variable label hasn't updated because we didn't update it. So okay, that needs changing. Sex and sex numeric are fine. Height in meters, yep, that's in meters. Weight in stone, no, that's not in stone, that's in kilograms, because we also changed that in the last exercise. So that also needs updating. BMI looks fine, BMI categories. Hair color, those are all fine. Systolic BP, yep. Diastolic blood pressure. Accommodation, yep. Exercise per week, calories consumed. Income, ran a marathon in the past year, and smoking status. We could, in fact, change the variable label of marathon, where 0 equals no and 1 equals yes, but we don't necessarily need to. So if you did that, well done. If not, that's fine. So let's do the two that need changing. We are going to label the variable of age to be age in years, no longer in months, good, and label the variable of weight to be weight in kilograms, not stone. And now everything should be up to date, and we won't get confused by thinking that someone weighs 79 stone. Or rather, most of the data set weighs about 70 stone. Good. Finally, save the data set. So I have changed the directory, so save, I can just type in save exercise 03 initials.dta and replace, because I'm pretty sure it already exists. And then it's going to crash. There we go. Sometimes my computer does that. That's not really a fault of Status, but the file says it wasn't found and it has saved, so good. Right, I hope you did okay with that. Any questions, let me know on Twitter. And yes, see you again in episode 4, lesson 4.